Okay, so we still have some time. So let me also get into the next topic, which is shortest path in unweighted graph. Okay, so the slides for this will be in the slides for the next lecture, lecture 12. Okay, all right. So we just talk about that using the so-called BFS, breadth first search, to traverse a graph, starting from a source node. BFS gives us a way to visit all the other nodes, a strategy to visit all other nodes reachable from the source node S. Okay, so that helps us to explore the graph. But sometimes you may want more than just exploring the graph. So for example, here's the flight map for some airline, and you say that, okay, can I reach, I want to go from Columbus to Denver, okay? So the first question is that, is Denver reachable from Columbus? Well, this question, we can use the BFS that we described just now to solve it. We just perform BFS at Columbus starting, and then we can ever discover Denver. That means we find a path, okay? So that's number one. But in general, you don't just want to know whether they are connected or not. You also want to find the best way to fly from Columbus to Denver using the fewest number of connections, namely fewest number of links, okay? So this means that you're looking for a path from Columbus to Denver in this map that has the so-called shortest length. Okay, in particular, recall that the length of a path is simply the number of nodes in this path minus 1, which is also equal, same as the number of edges in this path. Okay, so that's the length of a path. Okay, and the shortest path from U to V is simply a path whose length is the smallest possible. Okay, so for example, now if I have U going to U1, going to V, U2, let's say this is my graph, okay? And I want to reach from U to V. Well, the best way to go, I could go from U to U1 to V, or I could go from U to V1 to U2 to V. Clearly, the shortest possible way has length 2. So this red path is the shortest path from U to V. Okay. Now note that the shortest path may not be unique. I could have multiple ways, shortest way to go from U to V. In this particular example, I could also go from U to U2 and then from U2 to V. This is also a shortest path, both of them. So there can be multiple shortest paths from one node to the other, but they all have the same length. Okay, and this length of the shortest path is called the shortest path distance from U to V. So in this example, the shortest path distance from U to V is 2. Okay, all right. Now, also by convention, if there's no path from U to V, so basically V is not reachable from U, then we set the shortest path distance from U to V to be infinity. So that's just the convention. Okay, all right. So now the problem we want to solve is we're now going beyond just the traversing the graph. Okay, we're given the graph directed or undirected and the source nodes. Okay, and we want to compute the shortest path from the source node S to all other nodes in V. Okay, so we don't just want to visit all the nodes reachable from S, we also want to compute what is the best way to reach them from S. So this is our target now. Okay, now I should point out that unless I specify otherwise, in all this algorithm we're talking about work both for directed and undirected graph. Okay, so as you see in the BFS algorithm we just described, the difference is that the algorithm works exactly the same. The only difference is that when you refer to a neighbor of a node, when you explore the neighbor of a node by the adjacency list representation, for undirected graph, that's basically all the other nodes connected to this node U by an edge. While for direct graph, that's basically all the other nodes connected to U by an outgoing edge. That's it, okay? So the algorithm works exactly the same way, okay? All right, so this is now the so-called shortest path problem that we hope to solve. Note that obviously this problem can only be harder, it's at least as hard as the graph traversal problem, because now to compute the shortest path distance, we have to know whether we can reach another node. We have to explore all the nodes, right? So it's at least as hard as the shortest path, the graph traversal that we just described. The question is that can we still compute all the shortest path distance as efficient as just doing graph traversal. So that's, we want to be able to solve this problem efficiently. Okay, and that's what we're going to see next time. But today, we're just going to look at some example and also property of the shortest path. Okay, so here's one example. So here we're having, we're given a directed graph and the source node is S. Okay, and our goal is to compute shortest path distance from S to all other nodes in the graph. Okay, so that's what we want to do. Okay, now we started from S. Now note that S, the distance to the south clearly is 0 because I already found it. Okay, so I'm going to mark the distance here. And A and C, they're connected to S by one edge, which means that I can reach them in just by one edge. So their distance is 1, okay? And you cannot do any better, okay? So the smallest possible. Now we consider E, for example. I know that I cannot go to E in one step, okay? So the shortest path has to be bigger than 1. But then I noticed that, oh, I found a way to go through to E, either through C to E or through A to E. Both of them take only 2 steps, two hops. So the shortest path distance from S to E as such is 2, okay? The same for G. So the shortest path distance to G is 2, okay? How about F? Can I reach F in 2 steps? Can I reach here using 2 steps? No, right? Because I mean, to reach F, going to C, but I don't have 1 step, but I don't have an edge from C to F, okay? So there's no other way to reach F within just the 2 jumps, okay? However, we did notice that I can actually reach F using going from G, so there's 3 steps, okay? And this is the best possible because I cannot reach there using 2 steps. So the distance to F is 3. And the same argument essentially works for B and also for H. I can reach all of them in 3 steps. Okay, in fact, also to I, because I cannot reach them using 2 steps, but then I can reach them in 3 steps by going through one node that I already reached using only 2 steps. Okay, so this in the end is the shortest path to from S to all the nodes. Now suppose that I also have another, if I modify my graph, if I also add another node J, where this is the edge, I only have an edge from J to I, okay? So if this is what I have, then note that J doesn't have any incoming edges. There's no way for me to reach J from S. As such, the shortest path distance to J is infinity by convention, okay? So the problem that now we want to solve is that we're given a graph and we're given a source node S, and the output is what we computed here. I want to compute the shortest path distance from S to all other nodes, okay? All right, as I said, we're going to look at the algorithm next time, but first some properties of the shortest path, okay? These are very simple intuitive properties, but they're useful. The first one is that given any 2 nodes, U and V, okay, there are different ways to reach them, okay? So there are different ways to reach them, okay? And let's say that the shortest path is here. So let's say this is the shortest path, okay? The first property is that the shortest path has to be simple. Remember, a path is simple if no nodes is visited more than once, okay? So what is a non-simple path? So I could have the following. Let's say that this is a non-simple path. I first go to some node W, and then I'm going to visit W again, which means that I'm going to go somewhere and then come back to, so let's say this is all direct graph, okay? Then from V, I go somewhere, but then come back, I visit again. So it's not simple, and then continue to V. So this is not a simple path, okay? Now such non-simple paths cannot be shortest. Why? Assume this orange one is shortest path, and you present it to me saying that here, I found your shortest path, this orange one. And I look at this, I said, but hold on for a minute. If this is the shortest path, then I could have gone from U to W, and then directly from W to V. I didn't have to make that little loop, that detour you made. And my green path will still connect me from U to V, and it's shorter because I cut off your loop, okay? Which means that if you give me a non-simple path, I can always shorten it, okay? I can always shorten it by removing all these extra loops, okay? So I can always make it shorter. So a non-simple path cannot be shortest. A shortest path has to be a simple path, okay? So this is the first property, okay? The second one is the so-called optimal substructure property of the shortest path, okay? It's also very intuitive. What it says is that any subpath of the shortest path must be shortest path itself, okay? What does it mean? So suppose I have a shortest path. Let's say that this one first reaches W1, and then from W1 continue to reach W2, and then it reaches V, okay? Let's say I tell you that the green path is the shortest path, okay? If the green path is shortest path, then this path going from W1 to W2, this must be also a shortest path from W1 to W2. Okay, it has to be also a shortest path between the two endpoints. Okay, and why is this the case? Well, intuitively, suppose you say that, oh no, your red path is not the shortest one. Suppose you say the shortest way to go from W1 to W2 is the following. So the shortest one is going through the orange path, you claim. Okay, and you say the orange length is shorter than the red. Then that means that to reach from U to V, I could have, I say, hold on, if that's the case, then to go from U to V, I could have first go from U to W, and then from W to W1 to W2 using your orange path, and then continue to V. And this is also a path going from U to V, and since your orange path is shorter than my red, then that should be the shortest. Then my original one cannot be shortest. Okay, so this is a contradiction because I already know that my original one is shortest. That means that you cannot give me another way, this orange one, which is shorter. Otherwise, I could have used your subpath and make a shorter path going from U to V2. Okay, so all right, so that's what we said. So basically, you take the shortest path, and it's any subpiece, you take any portion of the shortest path that has to be shortest between its endpoints as well. Okay, so shortest path can only consist of many shortest passes. Okay, all right. So why is this useful? So this is a more precise. So here's one implication. So why is this useful? So here's a simple implication. What it says is that if you have a shortest path, suppose the shortest path going from U to V take K steps, has length K. Okay. That means that, so suppose this is my shortest path. Okay, so this is, let me draw so suppose this is my shortest path and has K steps, okay? That must mean that this shortest path is actually, and S is my so-called predecessor along the shortest path, okay? Then that must mean that this shortest path actually consists of first going from U to my predecessor S through K minus 1. So the shortest path distance to my predecessor has to be, so the distance to me is K, then the shortest path distance to my predecessor has to be K minus 1, okay? So it has to be that going from U first to my a node whose shortest path distance is K minus 1 and add one more edge to lead to me, okay? So, and this portion has to be shortest to S, okay? And you may say that, well, I mean, this looks really straightforward, of course. I mean, to get to V in K steps, I have to first reach somewhere in K minus 1 steps, add one more step, add one more edge, right? And what this is saying that the way that you reach this predecessor S in K minus 1 step, that has to be the best way to that as well, okay? So that's it. And how do we leverage this idea now? Okay, so in fact, it turned out that this is the key property that will help us to design the algorithm. And the algorithm is pretty much connected to our breadth first search algorithm. And we're going to do that next time.